What's going on, everybody? We've been calculating areas underneath the normal distribution, usually with a threshold somewhere in that distribution, a z-value, and we've been calculating the area to the right or to the left of that particular threshold. We've also been able to calculate what that z-value should be to set to a desired area underneath the curve. Today we're going to be applying that information to some various problems to solve. It's going to begin here with this particular problem in which we are taking a look at the number of liters of blood that exists inside the average human body. You can see here that the problem shows that an adult has an average of 5.2 liters of blood. Assume the variable is normally distributed. That means if you plotted it out as a histogram for all the people, it would look like a normal distribution. And it has a standard deviation of 0.3, and I think so find the percentage of people who have less than 5.4 liters of blood in their system. We can calculate this value, this percentage, according to our understanding of the normal distribution. So let's first take a moment for ourselves here and take some time. This is a time in which we're certainly being confronted with what it's like to be bored an awful lot, and in emptying your thoughts and in becoming completely alert to the present moment, it's a good way to battle that kind of boredom. So take some time, focus on your breathing, and get in touch with the complete now. Let's take a look here at this same problem. An adult has on average, let me actually pull this back here. Thought we had some warm-up problems. Oh, I put them in the wrong place. Let me pull these up, bring them forward. Here we go. Okay, so let's do these warm-up problems here first. This allows for us to draw upon the previous knowledge that we had before, in which I'm having you find some areas underneath the normal distribution curve. Here's a z threshold. This is going to be positive, so this is to the right of 0 here. But I'm asking you to find the area under the curve where z is less than 1.2. Same thing here with z being less than negative 0.54. Notice here, for these problems, I'm switching from lesser to greater from the left side of the distribution to the right side of the distribution. And in here, we're finding the area under the curve between these two values. And then lastly, we're trying to find a threshold somewhere along the normal distribution curve here, in which the area to the left of it, in other words, less than, would be 0.0749, or the area to the right of it would be 0.883, or the area between the middle of it and where it is to the right is 0.1950. So take some time to warm up using these particular problems here. Take some time for that. Welcome back. Well, this was a pretty intensive warm-up here that was testing a lot of skills from the previous lesson here. We were taking a look at finding areas to the left side of a curve from where z is equal to 1.2. That's taken from the table here where we look this up. Pull this up here. 1.2 is going to be right here, so that's 0.8849. You can see that right here. In the same way, if I draw that normal distribution here, with z being at 1.2, we were first finding the area to the left of that. That was this 0.8849. If we want to find the area to the right of that, in other words, the probability that z will be greater than 1.2, that's 1 minus this. So this portion right here is going to be 0.1151. All right, in the same way, if we're taking a look at this different location for the z value here, boy, my normal distributions are pretty messy. Let's see here. So negative 0.54, 0 right there, and we're trying to find the area to the left of that. So that's from our table going to be, let's see, negative 0.54. That's going to be 0.2946. So that's our answer there. Here we're trying to find the area under the curve to the right of negative 0.54. That's going to be 1 minus 0.2946, or 0.7054. And then lastly, this area over here, we are looking again at a normal distribution between these two thresholds. Let me put the 0 in here first. Here's 1.2 over here, and here's negative 0.54 over here, and we're trying to find the area in between these two. And so this, which we calculated earlier, is the area to the left of 1.2. So that's all of this area that you're seeing underneath the curve here, extending out to infinity in this direction. And this is the same thing, but just starting here and extending on to infinity. And so if we want to find the area in between the two, we have to take this first one and subtract off the second one. So our answer here is 0.3403. All right, and then lastly, we've got a normal distribution curve. We're trying to find a value of z. That's a threshold here. I just want to call it a capital Z just to distinguish it as a particular threshold. Z is less than z such that the area is going to be 0.0749. So if I draw this normal distribution again, I'm looking for some threshold here that's z, and I know that it's less than 0 because this is less than 0.5, so I know I'm on the left-hand side of this distribution here. But I want to find some value of z down here that gives me an area under the curve that is 0.0749. So I go to our handy-dandy table here again, and I look for 0.0749, and I find it here. And so that is, I need to see this top part here too, 0.0749, that's negative 1.44 on the normal table here. So negative 1.44 is the value of z on this x-axis here that gives us this area under the curve to the left of it. If we take a look at a different threshold here, we want to find the probability that z is greater than a specific threshold here. This is 0.8830. Now this takes a little while to draw here. Let's see. First of all, I'm looking at the area to the right of it, so it's going to be areas going in this direction, and we know that it's going to be on the left-hand side of this thing here, because in order for us to have 88% of the area, that's a lot. So it's going to be all of this plus a little bit more. Here's my 0. So z is going to be over here somewhere in order for us to get that 88.3% of the area on this side. So if this is the area on this side, if this here is the area on this side of z, then what's the area on this side of z, this opposite side? Well, this is going to be 1 minus 0.883, or 0.117. That's the area I have to look up on the table here to find out where z is. So 0.117, here it is right here. So negative 1.19 is the location of z. That gives me 11.7% of the area on one side and 88.3% of the area on the other side here. So that's our answer here for that one. And then lastly, we wanted to find a threshold here between 0 and some z that we don't know what it is yet, but we want this area right in here to be equal to 0.1950. Well, in order for us to look that up on the table, I need to know what the area is completely to the left of z, and so I'm going to have to take this area right here and add whatever this is. Well, this is just 0.5, since it's half the area underneath the normal distribution, and so this is, I'm looking for a value of z that has an area under the curve of 0.5 plus this, or 0.6950. So I'm going to look that up on my table here. .6950, there it is. So that would be 0.51, or 0.51 right here. All right, so let's take a look at those warm-up. After we've taken a look at those warm-up problems, let's take a look at some of these new applications that we have available to us. Here's an example here that I mentioned in the beginning. An adult has on average 5.2 liters of blood. Assume the variable is normally distributed and has a standard deviation of 0.3. All right, so let's see. Actually, I have this drawn here, right in here. So the average value of the amount of the number of liters in a person of blood in a particular person is 5.2 liters. That's actually, let's see, 1, 2, 3, 4, 5, a little bit more. That's actually pretty close to the amount of blood that's inside a human body there. So 5 liters plus a little bit more here. So here is the center of the distribution here, 5.2 liters. Some people have more, some people have less, but it's centered pretty much around 5.2 liters. It's normally distributed, so it has this particular shape, and it has a standard deviation of 0.3. So let's find the percentage of people who have less than 5.4 liters of blood in their system. 5.4 liters of blood, that's going to be somewhere over here. Oops, my bad. It's going to be somewhere over here. 5.4 liters. And so we want to know the percent of people who have less than that. So it's going to be, we're going to be shading in all the stuff here to the left of this. So we're going to be looking up values in a table. But before we do that, we have to translate this normal distribution that has a mean of 5 and a standard deviation of 0.3 to a standard normal distribution that has a mean of 0 and a standard deviation of 1. Well, how do we do that? Well, that's going to come up in a second here. But here's our standard normal distribution, and the way that we do this is we take all of our x values here. We have a particular x value here, that's the 5.4 liters of blood, and we want to know what that z value is. When we convert this to a standard normal distribution, now the mean is going to be 0, and the standard deviation is going to be 1. So here's the idea here. So we're just going to work now with this standard normal distribution, and the value of 5.4 that we saw here, this is our x, but we're going to find out where that threshold exists here on this standard normal distribution here. So we want to know where this value of z is on here. Well, how do we calculate that? We take 5.4 liters of blood, and we subtract off the mean. You can see I'm showing that here. So that's going to be 5.4 minus 5.2. That's the deviation from the mean. Let me remove my face here so you can see a little better. And that being the deviation from the mean, we have to divide that by the standard deviation, which is 0.3. So this is going to be 5.4 minus 5.2. That's just 0.2. And we'll just divide that off by 0.3. So it's actually this place right here in the previous, whoops. So what this shows is that this deviation right here from the mean was actually 2/3 of a standard deviation. 2/3 of a standard deviation. How do we see that? Because when we take the deviation from the mean here, it's 0.2, and we divide that by the standard deviation, that's going to be the same thing as 2/3, isn't it? So it actually, the z-value here is 0.67. So I'm going to put it right here. Okay, so this is now our standard normal distribution, and all we had to do was translate this x value into a z value using this formula. So this is a good formula to memorize here in going from these x values. Here's what our x value was. This is our threshold that we were looking at, 5.4 liters of blood in their system. And we wanted to translate that to a z value, which will be on the standard normal distribution. So here we are, our value is 0.67, and there it is. And we want to know, find the percentage of people who have less than 5.4 liters of blood in their system. We want to find the area under the the standard normal distribution curve here, where z is less than 0.67. Okay, so how do we find that? 0.67 here, 0.67, here it is, 0.7486. And so the answer is 0.7486 here. So z, the probability that z is less than 0.67 is this, which means that for our problem, 74.86% of people have less than 5.4 liters of blood in their system. It's good information if you're a vampire. So the procedure that we went through here is going to be the same procedure that you go through for each one of these problems. It's going to be pretty much the same. We first started off with drawing a normal curve and shading the desired area. That's actually something we learned in the previous section here, where we were drawing normal curves left and right. And then the second part here is converting the values of x, that's specific places on the normal distribution that's given to you, and translating those into z values, which are now on the standard normal distribution curve, using this formula here. Z is equal to x minus mu, so we're finding the deviations from the mean up here and dividing them by the standard deviation. And then lastly, finding the corresponding area using a table calculator or software. Here we're using a table. Here's another example. Newspaper recycling. Each month, an American household generates an average of 28 pounds of newspaper for garbage or recycling. This might be a little dated. Assume the variable is approximately normally distributed and the standard deviation is 2 pounds. All right. If a household is selected at random, find the probability of its generating between 27 and 31 pounds per month. So I'm seeing x values here already. I'm seeing thresholds. And then let's see, part B here, more than 30.2 pounds per month. Oh, that's another threshold. So let's first of all take a look. Let's figure out our normal distribution here first. We know that it has a mean of 28 pounds and it has a standard deviation of 2 pounds. Okay. And we also have these three thresholds that we can extract here. 27 pounds, 31 pounds, and 30.2 pounds. We're going to have to translate each of those into a z value. So here's Z1 from this first threshold here of 27 pounds. What does that appear? Where does that appear on the standard normal distribution? Well, let's see, 27 pounds. We're going to subtract off the mean, and we're going to get -1 here. When we do that, we're going to divide this by the standard deviation right in here, and we have -0.5. So the first z value on the standard normal distribution is going to be -1/2. Number 2 here. we have a threshold here of 31 pounds. What is that in the standard normal distribution? We want to take this value of 31 pounds and subtract off the mean. And when we do that, we're going to get 3. We'll divide that by the standard deviation, and we'll get 1.5 here. So that's our second threshold. Third one, we're going to take 30.2 pounds, subtract off the mean, and when we do that, we'll get 2.2. We're going to divide that by the standard deviation. That's going to be 1.1. So we now have 3 thresholds on the standard normal distribution. We're actually most of the way there now. So let's actually pull up our standard normal distribution right here, and let's plot some of these values here. Okay, so let's remember what these things correspond to here. We're wanting to find the probability of a household generating between 27 and 31 pounds per month. Between 27 and 31 pounds per month. Okay, so that's Z1 and that's Z2. We've plotted Z1 right here, and we've plotted Z2 right here. It's negative 0.5 and 1.5, and we're wanting to find the area underneath this part of the curve here. See how well I drew that? And so the way we can find that is to first of all find the area under the curve from here all the way to the left, and that's going to be 0.9332. That's from our table. And if we subtract off this area right in here, that starts here at this threshold and goes all the way to the left. If we subtract that off, then we can get 0.6247 for the probability that something is in between either one of these things. It's the area under the curve, it's the probability between these two thresholds here. So the probability of a household generating between 27 and 31 pounds per month is about 62% or so. And you found that by translating these thresholds into z values and placing them on the normal distribution, on the standard normal distribution. Let's do part B now. For part B, we translated this into a z value of 1.1. Here it is. And we want to look at less or more. Oh, it's more than 30.2 pounds per month. Okay, so we're looking at this part of the curve here. So the probability that z will be greater than 1.1, that's going to be 1 minus the probability that z is less than 1.1. And we can find this value on the table here. That's 1 minus 0.8643 or 0.1357. So in the context of this problem, there's a 13.5% chance that the household, oops, can't see me because of my picture here. So there's a 13.5% probability here that that household's going to generate more than 30.2 pounds of recycling each month. Do you think that companies like Waste Management, Gallegos, things like that are having to calculate statistics like this to plan for their capacity? Absolutely. They're having to work with this kind of data all the time. All right, so try this one here. A pediatrician obtains the heights of her 3-year-old female patients. This is actually a problem that I'll be referring back to throughout this entire presentation. I'll have you solve different things on it. The heights are approximately normally distributed, so she's measuring the height of each of these 3-year-old female patients with a mean value of 38.72 inches and a standard deviation of 3.17 inches. Use the normal model to determine the proportion of the 3-year-old females that have a height less than 35 inches. So we're going to use our standard normal distribution to find the proportion of the 3-year-old females that have a height less than 35 inches. Take some time for that. Welcome back. Well, this shows the power of what it is that we're doing here, and this allows you to solve these kinds of problems so easily. We come back to this, and we're seeing a normal distribution here with a mean of 38.72 and a standard deviation of 3.17. Well, where does a height of 35 inches sit on that? We know that it's going to be less than the mean, but by how much? It's going to be this many standard deviations away from the center. So that's the same thing as here on the standard normal distribution curve of this location right here, negative 1.17 on the standard normal distribution. And we're wanting to find the proportion of the 3-year-old females that have a height less than 35 inches. That's going to be the area to the left of this, which we can find from our table. Okay, here's another example. This same pediatrician with the same girls, find the probability that a randomly selected 3-year-old girl is between 35 and 40 inches tall. That is, find this probability right here. Take some time for that. Welcome back. Well, this is another problem in which we are looking at the heights of these 3-year-old girls, and as it turns out, we have now two thresholds that we're working with. It probably would have been a good idea for me to put x1 and x2 here so that we could label these as z1 and z2. That would be this threshold and this threshold here. So in a distribution that has a mean of 38.72 and a standard deviation of 3.17, where do these data lie here? This is less than the mean, this is greater than the mean, but by how much? Well, this first one is less than the mean by negative 1.17 standard deviations. So more than a standard deviation away from the mean here, less than that. And 40 in relation to 38.72 is 4/10 of a standard deviation to the right of that. So on the standard normal distribution, we can rewrite this, sort of redraw this as a range between negative 1.17 and 0.4 on this standard normal distribution, in which we've got a mean of 0 and a standard deviation of 1. And so here we're finding what this area is, and that comes from finding the probability of the area under the curve to the left of negative 1.17 and the area under the curve to the left of 0.4 here, taking one, subtracting the other, and we get 0.5344. So in other words, the probability that a 3-year-old girl is between 35 and 40 inches tall is a little over 50%. Okay, here's another example here. I'm actually showing this is Metallica up here, I'm kind of dating myself a bit here. This is James Hetfield, the lead guitarist for Metallica here, but decibels at a concert. A decibel is a measure of the intensity of sound. The average number of decibels at a full concert is 120. By the way, that's about the threshold where it starts to result in hearing damage, just so you know. Assume that the variable is approximately normally distributed and the standard deviation is 6. All right, so if 100 concerts are selected, approximately how many will have a decibel level less than 112? Sounds like we're dealing with a normal distribution here. So let's take a look here. We're going to eventually take this threshold and remap it as a z-value here on this standard normal distribution here. So how do we do that? Well, we take the mean and the standard deviation from this problem, and we have an x value here of 112. Is that going to be greater than the mean or less than the mean? All right, this is less than the mean, and so we know its z-value is going to be negative. Let's see exactly what it is. It's however many standard deviations it is away from the mean, that's what its z-value is going to be. So z is equal to 112, subtracting off the mean, this is going to be negative 8. So we know it's going to be negative now. Negative 8 divided by 6 is negative 4/3, or negative 1.33. Okay, so it's going to be over here somewhere. So we're being asked if 100 concerts are selected, approximately how many will have a decibel level less than, less than this. So we're looking at the area to the left of this. So what's the area to the left of this z-value? As it turns out, it's 0.0918. So that's the proportion of the curve that's on this side of it. And right now we're being specifically asked if 100 concerts are selected, approximately how many will have a decibel level less than 112? Well, if the probability is 9% and we have 100 concerts, how many of those concerts approximately are going to have a decibel level less than 112? It's going to be approximately 9 of them that'll have a decibel level less than 112. So in all of the problems that we've done up until this point, we've been taking, this is actually backwards. That's lovely. So this actually should say converting from z. Nope, I'm sorry, that's wrong. This is right. From x to z. So we're taking a threshold from the original normal distribution and changing that to a z-value on the standard normal distribution. But we're also going to have some problems here in which we are given a threshold on the standard normal distribution, and we have to change that to a threshold on the original normal distribution that we're given. And so let's manipulate this equation here so that we can solve for x. First, I want to multiply both sides by the standard deviation here by sigma, and so that's going to be sigma z, and I'm just putting this on this side now. And on this other side here, we've now multiplied, let me just draw this a little better here. We're multiplying this by sigma, and we're multiplying this by sigma. So you can see here on one side we've got sigma z, and on the other side these two sigmas are going to cancel, and what's left? I just have x minus mu right here. And how do I solve for x? I'm going to add mu to both sides. And here's our equation for x. X is equal to mu plus sigma z. Okay, so you will see how we're going to apply this particular formula in some of our problems coming up here. To qualify for a police academy, candidates must score in the top 10% on a general abilities test. Assume that the test scores are normally distributed and the test has a mean of 200 and a standard deviation of 20. Find the lowest possible score to qualify. So notice the threshold that we're given here isn't a score. We actually have to find out what that score is, don't we? So we're actually going to be finding, let's see if I can get my pen to work here. So we're actually finding what this threshold score is going to be. We're actually finding an x. How are we going to find this x? Well, we have a mean, we have a standard deviation, yes, and we also have something that will allow us to calculate a z right up here, the top 10%. Let's see what that looks like here. Okay, so we know that this has a mean of 200 and a standard deviation of 20, but we're not going to deal with that so much yet. Let's take a look at the standard normal distribution here, and let's ask, where is the threshold below which 90% of everything 90% of everything exists below it? In other words, if I draw my standard normal distribution here, we want to take a look at the top 10%. So that's going to be here somewhere, in which 10% of the area is to the right of this. We want to know what this threshold is. And it's going to be whatever threshold it is that the probability that z is less than this is going to be not 0.1, but 0.9. All of this over here is 0.9. So we're looking for a z value that gives us an area under the curve to the left of it of 0.9. And we can find that on our table. What we get is z is equal to 1.28. All right, so we know that this here on the standard normal distribution is 1.28. But how do we translate that to a score on the test? How do we find x from this? Let's think about this here for a moment. This 1.28 means that whatever this lowest possible score is, it is 1.28 standard deviations above the mean. So it's going to be bigger than 200 by this many 20s. And that's actually really all that this formula says that we derived in the previous slide here. We take the mean and we're going to add a little bit more. How many standard deviations are we going to add onto it? Well, about 1 1/4. Get rid of my picture here. 200 plus 20 times 1.28. That's going to be 225.6. So that's the lowest possible score to qualify for the entrance into the police academy. And again, for this problem, we were not given the x value. We were given this top 10%. So they have to score in the top 10% on a general abilities test. So first thing we did is we created our standard normal distribution. We just drew that like we always do. And we knew we had to find a threshold above which only 10% of people would score. So we had to find this z value here that had 10% of the area to the right of it. 10% of the area to the right of it means that there's 90% to the left of it. So we're trying to find a z value here that has an area under the curve to the left of it of 0.9. That is a z value of 1.28. So that's how many standard deviations above the mean this lowest possible score has to be. and we just calculated that using this formula. All right, here's another example using the same pediatrics situation here. Again, the heights are approximately normally distributed with mean 38.72 inches and a standard deviation of 3.17 inches. Find the height of a 3-year-old female at the 20th percentile. So let's think what that means here. 20th percentile, that means that 20% of kids are shorter than this person and 80% of kids are taller than this person. So think what that standard normal distribution curve is going to look like when you plot that out. So take some time for this. Welcome back. Well, this is illustrative of the fact that you're really getting an awful lot of information here about something when you just find the mean and the standard deviation. Just knowing that information allows you to calculate the height of a a 3-year-old girl at the 20th percentile. We could do this same calculation for finding out what the 30th percentile is, and the 80th percentile, and the 90th percentile. So we can see here that for the 20th percentile, those are girls that are just slightly above 3 feet tall here, just slightly above 36 inches here. All right, here's another example here. For a medical study, a researcher wishes to select people in the middle 60% of the population based on blood pressure, assuming that blood pressure readings are normally distributed and the mean systolic blood pressure is 120. You know how blood pressures are always two numbers. His blood pressure is 140 over something. The systolic is always the first number. The diastolic is the second one here. So this is the first of the two numbers here. So this is the amount of maximum blood pressure that you experience when your heart has just pumped one big pump and is sending a fresh stream of blood through your arteries, and so your blood pressure spikes up to this value here of 120. That's the systolic blood pressure. So assuming that blood pressure readings are normally distributed and the mean systolic blood pressure is 120 and the standard deviation is 8, find the upper and lower readings that would qualify people to participate in the study. Okay, this one's a little bit more complex because we want to find people in the middle 60% of the population based on blood pressure. We've got to draw this out on our standard normal distribution here to see what this looks like, the middle 60% here. How do we draw this? Well, let's take a look at our standard normal distribution here, and we're really looking for something that looks like this. We want to have the middle 60% here right in the center, and that's going to mean that the rest of the area is on the tails here. Well, if this is 60% and we have to divide everything else evenly between these two tails, that means 20% here and the other 20% here. And we just have to find the z values here that correspond to those areas. So let's actually take a look at that here. Let's find out what this z threshold here that has 20% of the area to the left of it. That's actually negative 0.84 right there. We actually saw that from the previous problem, in fact. So negative 0.84, I think we would actually find out that since this is symmetric, we would find that the location here will just be positive 0.84. So then what do we do with this? We've got z values. We need to find out what the values are on the actual normal distribution given in this problem, as opposed to this standard normal distribution, which we use in every problem. We're actually getting, the actual normal distribution for this problem has a mean of 120 and a standard deviation of 8. So where do these thresholds show up on a normal distribution with a mean of 120 and a standard deviation of 8? Well, here's where we use our formulas. Here's the first one here. We're going to work on this one to the left. 120 is the mean plus 8. That's our standard deviation times negative 0.84. That's going to be a blood pressure of 113. Let's look at the one to the right here. 120 plus 0.84. That's the positive side of this times the standard deviation. That's going to be a blood pressure of 126.72. That's our 60% distribution right in here. The interval here between this threshold and this threshold here. So 113.28 to 126.72, that's going to comprise 60% of the population there. So to participate in the study, each participant must have a systolic blood pressure between this and this. Oh, let me get rid of my, a systolic blood pressure between these two values here. All right, the SATs, another example of data that is very well distributed according to a normal distribution here. The scores earned on the mathematics portion of the SAT, it's a college entrance exam, are approximately normally distributed with mean 516 and a standard deviation of 116. So what scores separate the middle 90% of test takers from the bottom and top 5%? In other words, find the 5th and 95th percentiles. So it's going to be something very similar, except you're not looking at the middle 60%, you're looking at the middle 90%. with just little pockets of 5% in the tails on either side there. So take some time for this problem. Welcome back here. Well, you're getting some insights into what the ranges of scores are here on the SAT. We're looking at the math section here, which has a mean of 516 and a standard deviation of 116. But we can ignore all of that at first and just take a look at the standard normal distribution, and we're asking ourselves, how do we find the middle 90% of the distribution here? Well, the middle 90% is going to have 5% over here and the 5% remaining 5% over here. So we're trying to find the values of z that have just 5% prior to its to the left of its location here, and the value of z that just has 5% to the right of it. Let's take a look at the one to the left. That's going to be the z value that gives us a normal distribution area to the left. That's negative 1.64. We'll actually find that the same thing is true over here, except this will be positive 1.64. So we have enough now from the standard normal distribution to be able to find out what these scores are going to be here in this normal distribution, which has a mean of 516 and a standard deviation of 116. So the answer for the lowest level here is going to be about 1.5 standard deviations less than the mean, or 325.76, and this one's going to be about 1.5 standard deviations above the mean, which is going to be 700 or so. So the range of scores that we're dealing with between the 5th and 95th percentiles will be 325, 326 I should say if I'm rounding it, to 706. All right, so just summarize all that we've gone through today. Do you know how to do this? Do you know how to find the area under a standard normal distribution here? That's the stuff we've been using that table for. And second thing here, find the probability of a range for a normal random variable. That's another thing that we were working with. And then lastly, find the values of a normal random variable. That's where you had to find the threshold there. And we can do this for a variety of different problems. So you not only are getting some practice with these particular skills here, but also you're getting some skills with applying that to specific real problems here. So that's what we're discovering here as we're going through the normal distribution. This is a highly applicable part of statistics here, so hopefully you're enjoying this process and excited about all the things this opens up to you. I'll see you in class.